Thank you. Good morning. Can you hear me? Microphone is working. Okay, good. So I've been coding and programming for maybe a bit too long, a bit longer than I like to remember. I don't know, something like 20 years, maybe more. I start feeling old sometimes. I don't use Go in my professional, full-time, paid job. I do it as a spare time. And when I work in my spare time in programming, I want to have fun, because nobody is there paying me and nobody's there telling me what to do, so I want to enjoy it. And this little tool that I will present started as a kind of hello world, kind of let's see what Go looks like. And I can tell that I was satisfied with the result. Let's see if you are satisfied and you could be interested in using it. So I start with a question. Which ones of you know what code generation is? This should be an easy question. Okay, good. Which one of you actually used code generation tools in Go? Quite a lot of hands, a little bit less than before. Okay, good. Let's see. So, just for completeness, code generation, most of you know, we checked that you know, means that you write programs that generate other programs. Usually source code because it's easier, but you do other things. What is useful for? Computers are good at repetitive stuff, and generating programs is, in some cases, repetitive and boring. So if you have to generate a lot of variants of very similar and boring code, it's useful. If you have to generate, bindings to Marshall and non-Marshall stuff, and you want them to be very fast, so reflection is not enough, then you can use code generation to serialize and deserialize your structure, to Marshall them. If you want some compact specification of code, okay, I am a bit old school. I remember XML, SOAP, and bindings, but JSON has the same kind of problem sometimes. Or if you have, some definition, some binary protocol, and you want to define some high performance serialization, deserialization, or if you want to generate, an interpreter, why not? That's what I've done here. We will see how. And in any case, it's useful every time as we want to abstract not only what a program does, but what a program is. So what we do usually, I will try to be a bit quick on this because I guess most of you know very well this part. When we manipulate source code because we want to generate programs, we want to write source code, usually, at least in Go, we use abstract syntax trees. And for these three little letters, A plus B, the compiler somewhere hidden by itself, is not visible to you, generates a tree of structures. One represents the plus, and which is linked to another, which represents one of the operands, A and B, and so on. Well, in Go, we have some luck because this representation is included in the standard library, which is Go ast, and even normal programs can use it. This is the plus is a binary expression which contains the annotation is a plus. The A and B are identifiers. It's ast.Ident, and so on. So okay, they have a name. They have all the little details needed to make them work. I said usually it's hidden inside the compiler. You don't get direct access to what the compiler inside is doing. So if you want to do it manually, you have several options. One option is, okay, I create the structs myself manually. This is very painful, very long-winded, because for A plus B, you have to write, okay, the imports and then 4 or 5 lines of code just for 3 letters, A plus B. So you can imagine if you have to generate a lot of code with this approach, it gets really too verbose. Another example, x colon equal y. You define variable x, which initialize it with the value y. And if you want to represent the same structure that the compiler produces, abstract syntax tree, that will generate a source code for this, it's even more code. This is even a little bit abbreviated because there are no annotation about where in the source code was the identifiers were found and so on. So it's good, it's standard, but it's not really, really usable. It's really unreadable, really. So, better solutions. There is a very standard solution, which is the Go parser. It's, again, it's in the standard library. Then there are a lot of third-party solutions. You can write your own. GoGenerate actually invites you to write your tools that generate source code, but doesn't give that many tools to actually manipulate the abstract syntax tree. Yes, you have the walker and so on, the visitor pattern and so on. So, if you stick with the standard Go parser from the standard library, okay, a plus b is easier. Parser, parse exp, a plus b. Okay, as a string and does everything. If you want to move on, there are some obstacles. I guess you know, it was in one of the talks in the morning. You can parse an expression. Yes, that's example. You can parse a whole file. There is parse file. There is parse dir to parse a directory. There is nothing to parse a statement or a declaration. So you had to wrap them in something bigger, like a file, because you cannot parse them directly. There's no API for that. It's not that it's not possible, just not included in the API. So it's not really, really comfortable. There are other tools. This is a tool I checked around. It looks nice, but it has a little defect, in my opinion. I will dare to tell my opinion here because of what I like and what I don't. The main defect, let's say little defect, is that it's a custom representation. It's not the standard Go abstract syntax tree. So it's its own abstract syntax tree. So it's a bit more difficult than you have to learn another representation. The order is not so immediate to understand why you have to declare first the variable a, then the operation plus, then the variable b. And usually when you work with the abstract syntax tree, you work with the tree. So we start at the root, which is the plus, then the operands. There are others. For example, there is this one, which is very nice, which is a bit different topic, which is generics. It was mentioned already. I will not talk about generics in this case, but we are getting a bit on a parallel direction. So it's not really for code generation. It's for a more specific topic. So I want to show you my solution. It's not a new solution. I didn't invent it. I will have a question for you at the end of the talk. How do you generate the abstract syntax tree for a plus b? Okay, the solution I implemented is this. You write the symbol, the tilde, and then an apostrophe, and then you follow with your code. So your code uses the usual syntax that Go already uses. Inside the braces, you can put whatever you want, whatever Go code you want. It will be recognized. And what you get back is not the value of a plus b, but it's the abstract syntax tree a plus b. This means that the overhead, the additional code that you had to write to work on abstract syntax tree instead of just compiling it, it's really minimal because it's 4 characters. 1, 2, 3, 4. 2 if you don't need the braces. The other example, the x colon equal y, is the same. It's still staying the same tilde, same apostrophe, okay, the braces, and that's it. And it works. And I want to show it, I show you live here. If I do this. Can you read this? Shall I? Okay, maybe this is a bit better. Okay, should be able to read even from behind, from the back rows. So, okay, does nothing. Does nothing. Okay, so it's a ast binary expression. Let's check what's inside. Gets a bit more interesting. So it's a pointer to a binary expression. It has x, y, operation, and everything inside. The first element 0, it's the x, it's the first operand, and it's an identifier, which his name is A. It even recorded the position in the source code where it was stored, name, pos, and so on. So I created, with really, really minimal overhead, a little bit of abstract syntax tree. For the other case, or let me quit from the inspector. For the other case, assign x colon equal y. So yes, it works. Sorry. It looks nice. It looks like it does what it should do. So you have an array of left-hand side, an array of right-hand side. The left-hand side has one element. It's an identifier, which is x, recorded in a position in the source code, and so on and so on. So it seems it works. OK, so what am I doing? I wrote a language extension, which means I'm not using stand.Go toolchain. I'm using my own tool. This is Gomacro, which adds to the language this new syntax. What for? Let me step a bit back to tell what for, to understand what Gomacro actually is or is not. So it's an unofficial Go interpreter. It's a one-man project, me. Started as an idea to implement a Go interpreter with prompt, with read eval print loop, support full standard library, can load third-party packages at runtime with the plugin module, so it works only on Linux, Mac OS, no Windows at the moment, sorry. It supports almost full Go language. There are some little bit of missing parts if you try to play complicated tricks with interfaces defining inside the interpreter and so on. But it also has some interesting extension. One extension is a debugger. Another extension is one implementation of generics modeled after C++, not after the current proposal, because I wrote those before the proposal. If the proposal is accepted or looks interesting enough, maybe I can redo them with the official version of Go generics. And last extension, what we just saw right now, is code generation and macros. What we saw now is called quoting. OK, this is how to install it. It's a regular Go package. You just go get it. You can use it as arbitrary precision calculator if you want. It uses math, big integers if needed. All the untyped Go compiler support is there, and so on. Untyped constants and so on. What's really interesting, at least for me, OK, you can type normal code, functions, and so on. I will skip this part. You can basically you just type code at the prompt and it executes it. OK, I will try to do something really quick. OK, it's a function, and OK, it multiplies by 2. So you get something similar to the playground, but of course, this does not have the limitations on libraries and file system. Here, you can open a file, you can connect to the network, you can do whatever you want. You can import any library, and so on. what I am doing, that since I wrote my own interpreter, I was able to add extensions, which means, okay, I extended the syntax, which means since the compiler, or the interpreter in my case, has to build the abstract syntax tree in order to execute the code I write, I can ask him, please don't compile the code. In this case, I just want the abstract syntax tree, and I tell it with this syntax, tilde, apostrophe, and so on. And it gives me back the abstract syntax tree. That's how it's implemented. Then, okay, I show you already live this part. You can inspect and check that it actually built what you expected to build. Same for another example, the same assignment. Okay, so what actually is that I added to the language? These 4 operators and a bit more that we'll see later. First one, apostrophe, is quote. Second is quasi-quote. We will see how it works. And it works with the other 2, unquote, unquote splice. If some of you know some language, will recognize immediately these names. If not, it will be a question for you at the end of the talk, where they come from. It's not my invention. They have a big advantage with respect to other tools to generate source code, which, like, I don't know, the C preprocessor, which is that they respect the operator, let's say, precedence. We defined add before, it's still there, yes. We define multiply, which is, I had to use the quotes here, not the apostrophe, 3 times this strange syntax. Okay, let's see what happens. Ah, it worked. So, what does it mean? Let's go back here. When I say tilde apostrophe, it means take whatever is in the braces, give me the abstract syntax tree. When I say tilde quote, it means, okay, do the same. Don't compile the code, give me the abstract syntax tree, but if you find tilde comma inside, that part should be compiled and executed normally, and evaluated, it means. So it means don't put the identifier add inside the abstract syntax tree, but get its value and inject it into the abstract syntax tree. So which means it's 3 times whatever the value of add is, which is another abstract syntax tree. It was a plus b. So you are injecting a plus b inside the expression, inside the 3 times something, 3 times a plus b, because that's a value of add. So you are mixing building abstract syntax tree with normal code execution, normal code evaluation. Okay? When you do the double quote and say, okay, this is an abstract syntax tree, you go 1 step up to the indirection level. Say, don't compile this, give me the abstract syntax tree. When you put the comma, you come back down 1 step. So if you reach again the 0 step, the basis level, the ground level, then it means that will be executed. I'm talking about steps 1, 2, down, up, and so on. One very well known in the community that uses this is that if you use multiple quasi-quotes, it gets very, very hard to understand what's going on. Usually it's not very commonly needed, but in some cases it is. One thing that is automatic in this approach is that you don't get 3 times A plus B, because the abstract syntax tree already represents the precedence of the operators. So it's 3 times something, whatever it is. So the parentheses here, A plus B, are automatically encoded in the abstract syntax tree. So you don't have the same problems that the C preprocessor has when it does these combinations. There is one more operator, which is tilde, comma, at. I will skip a little bit because it's getting a bit long, which means insert not one thing, not one abstract syntax tree, but a list of them. And here, what I'm showing is to use a list of cases. Okay, this I said already. So this is a part of the aspect, the quoting. How do you quote? How do you get the abstract syntax tree for hello world? Okay, tilde, apostrophe, braces, and then you write a hello world. The only difference, this is not my fault, the problem is that you have to do something slightly strange there, with this tilde, func, and so on, because in Go syntax, when func is found as a keyword at the top level, it's either a function or a method. When it's found inside in the middle of the rest of the code, is a closure. In this case, we want a function, not a closure, because we want the abstract syntax tree that represents a function. So we had to tell it. So I had to introduce some new keywords, tilde func and tilde lambda, in order to disambiguate these cases. Because sometimes you want a closure at the top level, sometimes you want a function in the middle of the code. So you have to disambiguate, sorry. There was no way around. Same problem with type case. Sometimes you have to tell type case when it's a case on a type, when it's a type switch. Because if you do if you do case on tilde something, the parser will not know, and then you have to tell it. Okay, so what I showed you, how to get the abstract syntax tree from a compiler, actually from an interpreter, and manipulate it at runtime and do things on it. Of course, when you print it, there is all the support in the libraries, Go printer and so on, to print with the indentation and so on. So that's done already. It's not dumping it to the source file to be later on compiled. It's trivial. There is another part of the picture. Okay, what I've seen, in order to introduce it, we will go a little back to a little bit of compiler architecture very quickly. And at very high level, this is what a compiler does. Takes a Go source code, parses to tokens, parses to abstract syntax tree, then a big black box that compiles to assembly. Then the assembler compiles to object files and native language, machine language, and then you get your program. What I've seen with quoting is this kind of bypass. So instead of going through the compiler, you skip it, and you just preserve the abstract syntax tree, inject it in the assembly, and inject it in the user code. This is what quoting does. We can also do another very useful thing, which is, in some sense, the opposite, which is write a user program that manipulates abstract syntax trees, and we have seen already a part of it, but do it so that its output will be sent back to the compiler. Which means, okay, I have some source code, some Go source on the top. I do this loop because not all the source code that I want to be compiled is in the files. Some code will be generated on the fly by my program. I have a program that generates code, because this is talk about code generation. So I have some kind of magic, not so magic, actually it's just a function called macro that generates abstract syntax tree as an output. And that will be sent back to the compiler to be compiled as if it was normal source code, just it's generated on the fly instead of stored on the source code. So yes, it's a normal function. It's not so easy to implement in Go toolchain because it has to run at compile time while the compiler is running. So for example, it's not so simple if you are cross-compiling. Its input is source code. We have seen how to manipulate it. Its output, again, is source code because it's abstract syntax tree. That's an example. So you write macro, just the same syntax as func, is exactly a function. Its input must be a node from abstract syntax tree, or a class implementing that interface. Usually it's easier just to leave a node. Its output, again, is the same. So what it does, it takes the inputs, manipulates them whatever way it wants. It's just normal Go code. You can open a file, open a connection to Google, query, whatever you do. Import any library here. It's just normal Go code. Of course, plus the extensions that are available, which is quoting, quasi-quoting, unquoting, and so on. Here, what it does a quasi-quote where you get plus, which means the addition, binary expression for addition of the two arguments. It's very simple. In this case, you could do right by hands. If the code was very complicated, of course, you want to save it in a function. How do you use it? It really doesn't have a syntax. It gets the syntax from where you type it. So at top level in a interactive interpreter, you get statements or declarations. So you write it like a statement, which is separated by semicolons. So you have to write with semicolons. Add semicolon 1, semicolon 2. It's executed immediately. So it gets expanded, then it gets also compiled, and you get the result. The good thing about this, it looks a bit like generics, because here we don't deal with types. We only deal with abstract syntax tree, so it works with any kind of type that supports the plus operation that we put inside. So if we do on integers, we get integers. Actually, we have done that with untyped literals, because these are constants. When you write 1 and 2 are untyped constants, so the result is an untyped constant. If you do it on a string, you get the concatenation, because plus on strings or an untyped constant string is defined as concatenation. So it is a bit like generics. It's not really for that. It's just to generate arbitrary code. That's the point. It's different than generics. Okay, that's another example. This is a definition of a Fibonacci function, which is this: every term is the sum of the two previous ones, n minus 1 and n minus 2. You could write it as an example with normal code. We did it in one of the slides before, I'll show you. It's possible to get the abstract syntax tree for that. What we are doing here is that I write a macro that, when you execute it, it returns the abstract syntax tree to generate a Fibonacci function for whatever type is written there, because you have tilde, comma, and there it will be injected whatever argument you passed as the function call inside when you actually call the macro. Which means that if I call this make fib with int, I get fib for int. If I take for unsigned int, I get the definition for unsigned int, and so on. I'm just injecting pieces of abstract syntax tree inside other pieces of abstract syntax tree, manipulating those. What can you do with it? Well, basically anything. Because what you do here is that you have general tool to manipulate abstract syntax tree, and if you want also to execute it. But basically, the main use here is to dump it to a file and later on compile with a normal Go toolchain. Okay, this is an example when you run it. If I have enough time, I can type. Oh, I had to type it. Okay. Let's check. At least this part is shorter to type. Then just to show you that it's actually working. Okay, you get continuation prompt. Okay. Oh, I redefined add. Okay, okay, not a problem. It's working. So, yes, it's really working. Okay, this is an example. If I take the time to write this longer macro, then we can see that it really works. You can debug them either by telling the interpreter, please don't also execute, compile the result, the code produced by the macro, because I said that it will be fed back. It's not going back. Here. There is a way to skip this other part. It means, okay, I give you a user program. Execute my macro give back the compile, but don't compile it again, the result, the output, but just show me the output of the macro expansion, of the execution of the macro. This is called, in order to see what it produced, because otherwise it gets also compiled and executed and you get the result. And this is called macro span. Of course, there are other ways to debug code, Go code as usual, which means you can use print, and you can also use the built-in debugger inside my interpreter. Okay, what I have actually done, and this connects to the initial question, is what, in practice, what is it useful for? I've used my Gomacro as a preprocessor for Go, with this syntax, with these macros, with the quoting, unquoting, and so on. I will directly skip to the, okay, this refers to the extra slide, just to give you an idea of what it means. I wrote two interpreters. The first one was handwritten, 6,000 lines of code. It's very slow because it directly interprets the outside syntax tree, up to 2,000–3,000 times slower than compiled code. I implemented macros and quoting and so on inside that one, and I used that to write a second interpreter, which means that in the second interpreter, which is much bigger, 120,000 lines of code, 20% is handwritten, 80%, 81% is generated with the macros I explained. So 100,000 lines generated with those macros. Why? Because this second compiler interpreter, in order to be fast, instead of directly interpreting the abstract syntax tree, gives a first pass with all the type checks, creates a huge tree of closures that represent the program to be executed, and then execute it. In order to do this, you need to have in your source code a lot of closures. A closure to add two integers, a closure to add two unsigned integers, to multiply them, to call a function, to return, and things like that. So you really need a lot of macros, 100,000 lines. I can show you, just to give you an idea, I can show you some of the lines, not all of them, of course. Oops, sorry. To get an idea of what it means. For example, the binary operations. Okay, this is the code that does addition. Okay, the first case is quite simple. So if you want to add two integers, which means the reflect kind is an int, x and y are the two operands, are functions, must be called, and and you compose another function on top of them. And you have to write tons of this code, because you have to write for integers, unsigned integers, 8 bits, 16 bits, and so on. And all the combination, all the operators, and so on. So it's huge amount of code, very repetitive. Of course, for shift and so on. For constant, optimizing constants, because you evaluate them in advance, and so on. And, well, basically that's it. And one last thing I can tell you, that I wouldn't have done this second interpreter in some other way in my spare time, because it was too much code to write manually, and I would have stopped at the first one. So, okay. So you can download it from GitHub. This is my contact, and basically that's it.
We have a very, very little time for questions, so if any have.
No question, I scared them all.
Scary? I think it's just scary, yeah. And, well, after there is network time, so you can I think you can ask him. Just one thing, one service announced. The wardrobe will close soon. Will close at 6:30, 30 past 6. Okay. Okay. Thank you very much.